Dear students, as we have discussed earlier, principle of movement and center of gravity, today we are taking now the topic moment of inertia. Inertia, I think you are familiar with the inertia. Inertia is the tendency of a body to oppose a change in its state of rest or motion, and it is that property which is concerned with the mass of that body. Now the moment of inertia, what it is? It is the rotational analog of mass. Means if a mass particle is rotating around a fixed axis, in that case, its inertial property is concerned with the rotation of its mass about that axis. And in that case, in that manner, it is called the moment of inertia of that mass particle. Let us understand the moment of inertia of a body. As we know, if a particle is rotating about a fixed axis and its orbit of rotation is a circular path, in that case, it has linear velocity as well as the angular velocity. And the relation between linear and angular velocity, you are very well known with it, that is given by V equals to R omega. V equals to R omega, where V equals to linear velocity of particle describing the circular motion or the body which is rotating about the fixed axis, and omega equals to the angular velocity of particle or body, and R equals to the radius of circular path along which the particle is moving with respect to a fixed axis or fixed point. Since the particle is in motion, we can write down for its kinetic energy. The kinetic energy of the moving particle K equals to half mv square. Now, we are considering here that a particle is moving about a fixed axis. Now consider that a body is rotating about a fixed axis. In that case, all of the constituent particles of that body are moving around that fixed axis. It means the individual has their kinetic energies, they have their linear velocities, they have their angular velocities, and individual masses also. So in that case, for a system of particles, we can assign a relation for the kinetic energy of that body such that the kinetic energy of the system, means the body of particles rotating about a fixed axis, can be given as K equals to sigma Ki, where the value of I equals to 1 to n. It means the system or the body rotating about that fixed axis has its constituents particles, and the number of particles are n, and the sum of their individual kinetic energies is being considered here in terms of sigma Ki, where I is the ith particle of that body or system. The same can be expressed as sigma I equals to 1 up to n half mi vi square, where mi is mass of ith particle and similarly vi is the velocity of ith particle. In terms of angular velocity of the particle, the complete kinetic energy of that body can be rewritten as k equals to sigma from I equals to 1 up to nth particle of mi ri square omega square, where ri is the distance of ith particle from axis of rotation and omega is the angular velocity of each particle. Since all of the particles are being displaced here with the same angular displacement and their time period to complete one cycle is same, that's why the angular velocity of all the particles is same. So since the omega is constant, again we can write the energy for kinetic energy, the equation for kinetic energy, k equals to omega square by 2 sigma I equals to 1 to up to n mi ri square. Now the parameter here underlined by the orange color express the quantity known as moment of inertia of that body. So the kinetic energy of the body can be rewritten as half omega square I, where I equals to moment of inertia of body and is given by here I equals to 1 up to nth particle mi ri square. The parameter which is expressing here the moment of inertia of the body is independent of the angular velocity of the object. Now you can compare the same term of kinetic energy here with the relation of the kinetic energy half mv square, where omega is the rotational analog of the velocity, I is the rotational analog of the mass of the body. Let us consider this equation of kinetic energy of the rotating body as equation number 1. In translatory motion, in translatory motion of a body, we have an expression for the kinetic energy k equals to half v square m. Let us consider this as equation number 2. Comparing both equations 1 and 2, we see that there is an analogy between linear and angular velocity of body and between mass and moment of inertia of body. Let us consider one simple example to find the rotational kinetic energy of a body moving about a fixed axis. And we are taking here an example of a thin ring having radius capital R and its mass capital M. Let us take the example. Let us consider a ring of radius R and mass M rotating in its own plane with respect to uh, an axis passing through its circle center and perpendicular to its plane. The angular velocity of ring is omega. Thus, the linear velocity of each mass element of ring is v equals to r omega. Since the distance of each mass element is equal from the axis of rotation, so kinetic energy of the ring k equals to half m v square equals to half m r square omega square. See what we have written, underlining by orange color line, mr square, as we have considered that the kinetic energy of a moving body is given by half I omega square, where I is the moment of inertia. So as in general, k equals to half I omega square. Thus we can see that I equals to mr square for the ring, which is the moment of inertia of that ring with respect to its axis of rotation. So I think we have properly understood what the kinetic energy of a rotating body in terms of its linear velocity, in terms of its angular velocity, and in terms of its rotational analog of mass known as moment of inertia. So that's all for today. We will take the next topic in our next lecture. Till then, good day.